If you approach DAX as a spreadsheet language, your code will fail. DAX operates across an entire semantic data model. This is the tabular model. Data is strictly organized into tables, broken into columns, and linked by active relationship lines. Within this architecture, DAX calculations live as physical columns grafted onto tables, or as floating equations known as measures. New developers often attempt to force standard spreadsheet math into this environment. They try to reference specific row numbers, or write formulas expecting a static grid. Mastering DAX requires you to separate static data stored at rest from dynamic equations executed at query time. Failing to distinguish between static storage and dynamic execution results in calculations that return incorrect figures and models that eventually fail to scale. To prevent the engine from confusing these two execution states, DAX enforces a strict syntax standard. These rules do not just make the code readable, they instruct the engine exactly how to process a variable. When referencing a calculated column, you must include the table prefix, like sales quantity. For a measure, omit the table name entirely, like sales amount. Remember, table prefix means static column. No prefix means dynamic measure. Following this standard guarantees that anyone reading your code immediately knows the execution context of the variable. As calculations grow complex, knowing instantly whether a value is static or dynamic prevents calculation errors during context transitions. A calculated column evaluates exactly once per data load. It evaluates at data refresh time, long before a user ever opens a report. The engine iterates through the table, computing the formula row by row, locking in the result for each specific record. Once computed, those results are materialized. They are compressed and stored permanently in the server's RAM. Because this data is static, it will never react to a user clicking a slicer or filtering a visual. The values are fixed until the next scheduled data refresh. Therefore, calculated columns are required for creating new categorical attributes, like grouping prices into high, medium, and low buckets. Using them for analytical metrics wastes physical memory and limits interactivity. Measures operate under the exact opposite constraints. They do not compute during a data refresh. They evaluate at query time, reacting the millisecond a user interacts with a report. Because measures are evaluated on the fly, they possess no inherent awareness of individual rows in a table. They only understand aggregate selections. This matrix shows sales amounts and color counts sliced by different product brands. Look at the intersection for the brand Contoso. The measure calculates $2.2 million. It does this by dynamically filtering the entire database down to just the Contoso records, and then running the calculation on that specific subset. We can prove this is a dynamic evaluation by looking at the total row. It shows 16 colors. If DAX were simply adding up the rows above it, the total would be 120. Instead, DAX evaluates the total independently, counting the unique colors across the entire unfiltered dataset. Measures act as the dynamic engine of interactive reporting because they adapt their underlying mathematics to the visual's filter context on the fly. This presents a functional hurdle. If a measure has no row awareness, how do you multiply the quantity of an item by its net price inside a measure? Standard aggregators like SUM are designed to scan a single column and return one value. If you try to pass an equation like quantity times price into a SUM function, the engine throws a syntax error. It cannot process multiple columns at once because it cannot see the rows required to match them up. To solve this, the DAX engine uses a specific class of functions called iterators, in this case, SUMX. Iterators require two specific parameters. The first parameter dictates the target table you want the engine to scan. The second parameter is the expression to evaluate. Because the iterator establishes a temporary row context on the target table, it can execute math across multiple columns. The execution happens in two distinct steps. First, the engine scans the table, calculating quantity times price for every single row. Second, it takes all of those temporary results and aggregates them according to the function's prefix, in this case, summing them together. Iterators bridge the architectural gap. They safely inject row-by-row logic into the dynamic, memory-efficient query space of a measure. Functions in DAX are divided into two main categories. The first are scalar functions. These evaluate data and return a single definitive value, like a string of text or a numeric total. Both standard aggregators and iterators fall strictly under the scalar umbrella, as their ultimate goal is to output a single number for the report. The opposing category consists of table functions. Instead of returning a single number, these functions return an entire table of data. Functions like filter, the all function, and the values function scan the model and generate temporary grids of data entirely in memory. While scalar functions plot the final numeric point on a dashboard, table functions build the invisible scaffolding that isolates and shapes the data before it is ever counted. This brings us to a strict architectural reality. A table function is almost never the final output of a DAX measure. Because a measure must return a scalar value to display in a chart, table functions are used internally. They act as structural filters, feeding precisely shaped tables into the first parameter of an iterator or a calculation. This powerful internal shaping mechanism dictates exactly what data the measure can see at any given moment in time. Understanding columns, measures, iterators, and tables is the strict prerequisite to controlling the DAX engine's central mechanism, the filter context.